All right. Welcome everyone to, I guess this is the third session of Euclid's Elements. So we got up to proposition 3 last time. So Kenneth's going to kick us off with proposition 4. So it's all yours,
Cool.
Kenneth.
All right. So yeah, sorry for missing last week due to time confusion. I guess we're up to proposition 4. So let me uh let me just write down the thing and draw the pictures, and I'll give a quick proof. So proper wait, what? Hang on. I must be on black. There you go. I was on black. Undo. Okay, so proposition 4 has to do with this is probably something that we've all used in high school geometry, right? You're given two triangles. I'll draw the pictures first and I'll give the statement. So you're given two triangles like this. So I'm glad I don't have to draw circles today because I tried it out and I wasn't very good at drawing circles. So A, B, and C for the first triangle. And the second triangle is called D, E, F. Yeah, well, I can't erase, so unfortunately, it'll just have to be whatever it is. So, the hypotheses are that I'll just mark the size. So AB is equal to DE, and AC is equal to DF, and the included angle of these two sides are also equal. And the conclusion is that if these three things are true, then the triangles are the same, right? So we let the statement is you let ABC and DEF be triangles, right? With the mentioned size being equal, AB is DE, AC being DF, and the angle in between, which we call BAC, and EDF are being equal, then I guess the main claim is that the triangles are the same, or what we call in modern terms congruent, right? But I guess to follow Euclid, he kind of breaks this down into four separate statements, right? The claims are that one BC equals CF. So the other side, the third side that we haven't explicitly said as being equal are in fact equal to the triangles are the same. ABC uh, is is equal. I'm just going to say is equal to triangle DEF, and he also adds two more statements, right? Just to say that the other two angles are also equal. So ABC is equal to angle DEF, and for the ACB, right, is equal to angle DFE. Okay, so the proof of this is using a technique that we probably haven't seen used in Euclid before. So the terminology he uses for it is to apply one triangle onto the other, which, as far as I can tell, means you put one point when we start with A, and we put it on D, and we line them up. Line up the points, and then we line up the sides A, B, and D, E, right? And then we kind of argue from putting the triangles and maybe superimposing them on one another that they're exactly the same triangles. And so to me, this kind of reminds me of like doing some kind of translation, but he obviously doesn't use this terminology here. So we let uh, I guess let the triangle ABC be applied. I'm going to put this in quotations to the triangle DEF, and there are some notes in the text that says that this should be thought of as another postulate that we can do this. So So this is not strictly using something that we mentioned in the postulates that maybe Daniel's talked about in the last 2 weeks. So what this means is that we place the point A on point D, and the line, and place the line AB on DE. Okay, so if we can do this, right, then B will coincide with E. And again, we see this this terminology of coinciding with E, right? And since, right, this is because AB is assumed to be equal to DE, right? So AB is one of the equal, well, AB and DE is one of the pairs of equal sides of these two triangles, right? Right. So if you place a point on another point, you place the lines going in the same direction, then going from A to B is the same as going from D to E is the same length. So the point B must be the same as the point E. Okay, so that's the first argument. I'm going to shift to the second board here. Right. So once we have that, now we're gonna argue that the other point C and F are also coinciding. They're also the same point if we do this application of one triangle onto the other. And so we're going to argue that since AB coincides with DE, right? So that's the line AB and the line DE, right? Pointing in the same direction, coinciding, sharing a point, so they're the same line, and the angle. So now we use the fact that the angle in between are the same. BAC is equal to angle EDF. Then AC, right? So this is line AC, coincides with the line DF. And so similarly, same argument as before, C coincides with F. Okay, so we have these two statements now, right? B coinciding with E, I'll just underline it here, and C coinciding with F, right? And the final bit of argument here is that since these two are really the same points, once we move the triangle so that they're on top of each other, and using proper postulate 1, then there's really only one line between them, or as he argues in the text, that if these two lines from B to C and E to F are not the same, then there'll be a space. Then the two lines will enclose a space, which is impossible, right? So now, if BC does not coincide with what was it, EF, right? So the two base sides of the triangle, then you have this situation happening. They kind of had this in the text, right? Like you have a line here and then a line here, right? They're both straight lines, and there'll be a space in between, right? And that's what is claimed to be impossible, right? Then the two lines.
Yeah, I find this a little weird somehow. It's kind of he's actually justifying the postulate intuitively here. It's not really part of the
Right.
proof, right? I mean,
Yeah.
this
So
is a postulate that this is impossible, but he chooses to draw it in such a way and appeal to your intuition about space in some kind of. It's basically extra rig. I mean, beyond rigor, right? It's not. It's not actually a part of a justification.
right, yeah. So one of the footnotes in the book, the other footnote associated, this is basically said that, well, postulate 1 really says that there's a unique line. you interpret it saying there's a unique line between 2 points, then you can just say that instead, right? But then that wasn't really. I mean, the postulate on its own, it just says there is a line, right? It doesn't say the line's unique. And I guess this is kind of saying, well, there's only one, right? Of course, this only works if you're on a flat space, right? Um, I mean, not flat. I mean, Euclidean space, right? You can think of examples where this isn't true, and so right. And so the final kind of thing is to say that, well, um, we used several times here that this common notion that was. I don't know, Dan, if you mentioned these common notions, but there's this. We keep using the word coinciding, which is kind of whatever that means, right? But like the common notion that we use is that things coinciding with one another are equal. So yeah, so I guess in some sense, I feel like he's using kind of arguments that probably can be made more rigorous if you have coordinates, right? You're putting a point onto another, you're kind of like just translating, right? That's easy to do if you have coordinates. If you don't have coordinates, you have to just say something like you put one point on another, and then you kind of rotate the triangles in such a way so that, right, A lines up with D, and then the lines are now pointing in the same direction. Well, they must be the same line. You go a certain direction in this line, the same direction, you land in the same point. And so eventually, right, with all of these caveats, we get to the very familiar kind of test for congruent triangles, SAS, right? You've got two sides being equal and the included angle being equal, and the triangles are then congruent. So cool. I think that's it. I'll put a little box here, right?
I guess Billy would say that using coordinates in that way is confusing the theory with the model potentially.
Right.
But yeah. Okay, is it my turn?
Are you guys still there? Oh, cool.
This is, I guess, kind of a converse to Proposition 4. So Proposition 4 says if two sides and the included angles are equal, then the rest of the triangle is equal. Triangles are equal. Proposition 5 says the following. So I'm over on the other board now. So it says for isosceles triangles, triangles, the angles at the base are equal to one another. So the diagram is the following.
So proposition 5 says that for isosceles triangles, the angles at the base are equal to one another, and if the equal sides are produced, then the angles under the base will be equal to one another. Right. So I'll keep writing, I guess. Under the base will be equal to one another. Okay. So right. So that's just a statement, I guess. So let ABC be the isosceles triangles. That's the isosceles triangle with base having AB equals the side AC, which is as written. Right. So I think I'll just talk through the labeling of the triangle and just draw it on a diagram, and then I'll get to the proof. So right. So AB is equal to side AC, and then let the straight lines BD and CE be produced as straight line in a straight line with AB and AC. So I guess we kind of extend these out down here, right? And then we call this D and E, right? And right. So we can do this because postulate 2 says we can. So we say that the angle ABC is equal to ABC is equal to ACP, and angle CBD is equal to angle BCE. So right. So basically, right, it's just you just want to, so you say that these two angles are equal, and that these two angles are equal, right? I think that's it. Angles and it's equal size, right? So that all makes sense, right? And so the proof goes like this, right? So you let the point F be taken somewhere on BD. So we let a point, the F, right? Oh, you can't erase it. Let F be a point on BD, right? So I'm going to call this F right here, and let AG have been cut off from the greater AE equal to lesser AF. Also, let the straight lines FC and GB be joined. So I think what we want to do is we want to have a point G here, which is the same as the length of AG is the same as length of AF, right? And then we join up these points here. I'm just gonna draw these like that, right? And and G on A B D on CE, right? Right, such that I think what they want is an AG being cut off such that I think AF is equal to AG. Right. Right. And so since AF is equal to AG, right, and AB is equal to AC, right, which is by hypothesis is equal to AC, right? The two straight lines FA and two straight lines FA and AC are equal to the two straight lines GA and AB. So we want to say that we have FA. I guess I've called it AF, so I'll keep it as AF. AF is equal to GA. Wait, isn't that what we just said? Sorry, I'm reading this. I haven't read this before. I'm getting a little bit confused by what they're saying. I'm just gonna follow it, and maybe you guys tell me if it doesn't make any sense. All right. So FA AC are equal to GA and AB. Right, so they also encompass a common angle FAG, right? Common angle FAG. So the base FC is equal to the base GB. So is there a next board on the side? We can, yeah, we can do it here. Right, so hang on. Get to the board here. So FC is equal to GB. Okay, so let's make sure that this makes sense. So FC is the line that we drew from F to C, right? That's underneath the triangle, and GB is the other line, right, from the other side. And so these are also equal. And the triangle AFC is then equal to the triangle AGB, right? And the triangle AFC is equal to the triangle AGB. And the remaining angles subtended by the equal sides will be equal in the corresponding remaining angles. So I won't write that down. So this is essentially just a proposition 4, right? Using the fact that SAS and triangles are then congruent. And so, right, since AF is equal to AG, and AB is equal to AC, right? Then BF is equal to CG. So I think here you're just subtracting intervals of lines, lengths of a line that's contained another, of subtracting the length of one line from another, right? And so this is using one of the common notions that we would have mentioned before, right? But FC is equal to GB from before. So the two straight lines BF and FC are equal to CG and GB, right, respectively. And the angle BFC is equal to the angle CGB. Okay, going back to the diagram, BFC, right, is this little small triangle under the big triangle that we had, and CGB is the triangle on the other side. And so, right, and so again, we're going to use proposition 4, right? So by proposition 4 from before, hang on, give me a sec. Where am I up to? All right, so the angles are equal, and angle BFC is CGB. Okay, and so yeah, by proposition 4, right, the triangle BFC CGB. Okay, so therefore FBC is equal to so I think it's triangles FBC is GCB and BCF to I think this is the triangle. Hopefully it's not the angle. I'm not saying this is the wrong thing. Of course, I can check the diagram and just very quickly verify this. C, B, G. Okay, let me just check and see if that makes sense. FBC. Okay, yeah. GCB. Okay, that all makes sense. Okay, so we've got these triangles being equal. Therefore, since the whole angle ABG, oh, not say therefore again, right? So since the whole angle ABG was equal to the whole angle of ACF, right? Within which angle CBG is equal to angle BCF, the remainder ABC is equal to the remainder ACB. So again, I think here we're subtracting angles from one another, right? And so one of our common notions allows us to do this. So they are at the base of the triangle ABC, and FBC was shown to be equal to GCB, and they're under the base, right? So therefore, for isosceles triangles, the angles of the base, right, are equal, and the angles under the base are also equal, right? So the last sentence here is just a recapitulation of what we were trying to show earlier. So sorry I rushed through that a little bit because I have a hard stop at I guess 11 o'clock for you guys. Is Dan really gone? Is he?
No,
Is kind
I'm
of?
back now. Thanks, Kenneth.
Oh, okay, cool. Okay, cool. So sorry I had to rush that a little bit. I have a meeting at 4:11, so I gotta run.
Yeah,
But
thanks for
hopefully that
taking
was
over.
more or less correct. Cool. I'll be back. I'll be back in about half an hour.
Great. Okay, see you then.
Cool. Cheers. Bye bye.
All right, everyone. So let's head over to the venue for the foundation session.